Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, folks, why don't we get started? I know we're still 2 minutes early of our traditional time, but I think we have critical mass and we'll just punish anyone who shows up late. So I'm pleased to introduce Prince. Prince, of course, is from UT Austin, one of Mike Delean's students there. I guess Mike and Lorenzo are really together, right?
Yeah, I mean, like Mike was my primary advisor.
Okay. Actually, Prince is not a stranger, though, to MSR. Prince interned with us back in 2004, working with Galen on Singularity. More recently, he's actually done an internship with our colleagues in Silicon Valley, working with Ted Waber and Doug Terry and other folks there. So he knows something about MSR. He's with us here today and tomorrow interviewing for a postdoc position. So welcome, Prince.
Thank you. So thanks, everyone, for coming. So today I'll be talking about cloud storage with minimal trust. The bulk of this talk is going to be on a system called Depot, which attempts to embody this philosophy. Towards the end of this talk, I will also talk briefly about some ongoing work on sort of bridging the gap between ACID distributed databases and sort of these data stores that provide a way to implement based on that base sort of workflow. So let me start by talking about Depot. So Depot is a cloud storage system in which clients do not have to trust, that is, assume the correct operation of storage servers or other clients. So to motivate this model, consider the example of a hypothetical picture sharing website called CloudPick that uses an external storage service provider, such as Amazon S3, to store its data. So whenever the user has to store new pictures, CloudPick simply pushes them to the SSP, and whenever the user wants to access its pictures, CloudPick fetches these pictures from the SSP on demand. This model is appealing because the SSP handles all the details that are necessary to build a highly reliable storage. Details such as geographic replication, scrubbing latent errors, provisioning for load spikes, etc. And because of economies of scale, it can do so at a very attractive cost. So considering these benefits, it should not be surprising that a lot of people have adapted this model over the last few years. Despite these benefits, however, I argue that there remain significant risks associated with cloud storage. The first one being that the cloud storage is a black box to its users or its clients. The users are not really aware of what are the best practices followed by the storage or what are the key replication policies that are implemented to ensure reliability. So when I store an object onto the storage service, I don't necessarily know whether if it's going to be geographically replicated or not, and if so, then at what granularity? Is it going to be replicated to multiple sites within a few seconds, within a few minutes, within a few hours, or at the granularity of days?
Sites publish their policies on that, so often you do.
Yeah, but you don't necessarily know. These are, for example, for geographic replication, you don't when you push something to Amazon S3, you don't necessarily know if it's immediately going to be replicated at 2 nodes, and then gradually it's going to be replicated to maybe 3 nodes, and if so, then at what granularity that is going to happen. So the policies are maybe there at some level, but they're necessarily vague, perhaps for a good reason.
I'm sure you get that. Okay, all right.
So the second challenge with the cloud storage is that, like any distributed large-scale system, cloud storage are complex. They're prone to both software failures, hardware failures, and failures that result from external factors such as natural disasters. And sort of like the repeated occurrence of outages in these large-scale services certainly does not help user confidence in these services. So the key challenge, the key problem with in using cloud storage, I argue, is so at this point we have a conflict. On one hand, the cloud storage offers numerous benefits, but on the other hand, there are certain risks associated with using a cloud storage service. And I argue that the fundamental reason behind this conflict is trust. So at this point, cloud storage services are not entirely reliable yet, but still we trust them. We trust them with the durability of our data. We trust them to remain available whenever we want to access our data. And we trust them to provide the right data whenever they send any data back. So in this work, I'm going to argue for an approach of minimizing trust. So what I mean by that is that we want to minimize our assumptions about both the correctness as well as availability of the storage service. What this means is that while we expect that usually the storage service will return the right data, we should be prepared to handle situations when the data it returns is potentially inconsistent, or situations where the data is corrupted, or even situations when the storage service becomes unavailable. So let's see how something like this can potentially be implemented. So our goal is really to enable the client to be able to separate good data from the bad data. So whenever the cloud service responds back with the data, if the data is correct, the client will end up accepting it. However, if the data is incorrect or potentially inconsistent or corrupted, the client will be able to reject that data. Furthermore, to handle situations where the cloud service becomes unavailable, we want to enable the client to specify what replication policies it wants to implement. So for example, the client might want to use multiple SSPs, or it might want to keep a local copy of its data in its local data store, and it should be able to access either of these stores transparently without having to compromise consistency or correctness. So I argue that this approach would be appealing to both the users as well as the SSP. The reason it will be appealing to users is because they can sleep peacefully at night, knowing that the failure of the SSP overnight will not make them bankrupt. And this increased trust can translate into increased cloud utilization, which can in turn translate to greater revenue generation. So the key question, however, remains that can we actually build a useful system despite these weak assumptions? And the answer turns out is yes. We have built a system called Depot which embodies this approach. It's a key value store similar to Amazon S3. And in this system, clients do not need to trust the servers. As a result, the system can continue functioning despite routine failure of a single machine, correlated failure of multiple machines, or even situation when the cloud service goes down. And we also further tolerate situations where some of the clients might behave arbitrarily. Perhaps surprisingly, despite these weak assumptions, Depot is able to provide stronger properties than those provided by existing highly available storage deployments. In particular, Depot provides a variation of causal consistency on each of its volume. In contrast, Amazon S3 only guarantees eventual consistency. Furthermore, Depot is able to ensure availability despite fail-stop, corruption, or correlated failure of a set of machines. And Depot is able to guarantee durability despite correlated failures of machines in the cloud. So in the rest of the talk, I will basically consider three key properties that Depot provides: the property of correctness, availability, and durability. For each of these properties, I'll explain where the trust lies in existing systems and what is the key goal of Depot in terms of minimizing that trust. Then I will explain what are the key techniques that Depot uses to achieve this goal of minimal trust. Finally, I'll come to the point where I'll discuss what is the cost of achieving this minimal trust guarantees in Depot. So let me start by talking about correctness. So in an existing cloud storage service, whenever the storage service returns an answer, the client expects that the answer will be correct. So that's where the trust lies. Yes?
When you say client, do you mean Yelp or do you mean a customer of Yelp?
Right. So in this case, we talk about the enterprises that use the storage service. So that will be Yelp. All right. So whenever the client receives an answer from the storage service, it expects that the answer is going to be correct. And so in some sense, it's trusting the service to return the right answer. As a comparison point, in traditional state machine replication or quorum-based systems, the client trusts that whenever a quorum of machines return matching responses, the response is going to be correct. In contrast, the goal in Depot is to eliminate the need to trust either the SSP or the other client. And we're going to achieve this goal by enabling the client to distinguish good data, correct data from incorrect ones. Now, in order to go further, I need to first define what it means for a data to be correct. And so I'm going to do that by defining the consistency that Depot provides. So this diagram here depicts the spectrum of consistency semantics that are provided by existing systems. On the extreme right-hand side, we have very strong consistency, which is provided by systems like Azure, Megastore, potentially Bigtable, and so on. These semantics offer a very intuitive property that each get that you perform is going to return the result of most recent put that was performed to that object. However, some fundamental trade-offs prevent us from achieving these properties with high availability and minimal trust. In particular, CAP theorem argues that you cannot achieve strong consistency without compromising availability. And similarly, the trade-offs for Byzantine agreement argue that you cannot achieve this property with minimal trust. On the extreme side, we have on the extreme left-hand side, we have systems like Amazon S3 or Dynamo that provide very weak eventual consistency properties. These properties are achievable. However, they're very weak, and they make the task of programming very difficult. And the key reason is that these systems do not provide even a very simple property that programmers expect, that if as a programmer I perform a put and immediately after I perform a get and no other puts happen in between, I would expect that the get will incorporate the result of the put I just performed. But these systems don't guarantee this property. As a result, hackers have to sort of build in like artificial best effort mechanisms by adding artificial delays, hoping that the replication happens within this period of time, and so on and so forth. Furthermore, these semantics do not prevent dependency of puts that are performed by the by the client. So, for example, if the client reads the result of one put and then performs another put, potentially depending on the first put that it read, these systems do not guarantee that these two puts will be observed in the same order by all the other clients. So, to address these limitations of existing semantics, we have basically designed a new consistency semantic that is called fork-join-causal consistency. Our goal with fork-join-causal consistency is to be able to retain to provide the strongest possible semantics that can be provided with high availability and with minimal trust. So, fork-join-causal consistency is a slight technical weakening of causal consistency, which is designed to accommodate environments where we need to minimize trust. And in particular, fork-join-causal consistency retains the essence of causal consistency. That is, it provides the property that if a client performs a put and then performs a get and no other operations happen in between, the get is going to return the answer of the put it just performed. Similarly, if there are two dependent puts, they will be observed in the same order by all the other correct clients. And this property can be useful for a number of reasons. First, it sort of makes sure that the expected behavior of the system, it improves user experience because the expected behavior of the system sort of matches the real behavior offered by the system. Secondly, it makes the task of programming easier because suppose that I add a new object and then I add a reference to this object, I'm guaranteed that the reference will not be seen without the original object that I added. And finally, it also helps us in layering other properties on top of fork-join-causal consistency.
So the gaps are the places where it gets weaker than causal consistency is that if somebody else adds an object and then you add a reference to that object, you may not be able to guarantee that the reference is valid. Is that the...
No, that's not the... So you still get that property. Actually, so it retains most of the properties that causal consistency offers. The way in which it is weaker than causal consistency is that in causal consistency, you have an expectation that all the operations performed by a given client will be totally ordered. Whereas, because if clients can be arbitrarily faulty, then you cannot uphold that expectation in this environment. So for clients that are faulty, this total ordering property is compromised. But those dependencies are still preserved for all arbitrary scenarios. So to illustrate the benefits of fork-join-causal consistency, let's revisit our example from before. So suppose that me and my advisor use this hypothetical picture sharing website to share pictures. Now, suppose that the system right now is just eventually consistent. So recently I went on a secret trip and I didn't want Mike to see these pictures of this secret trip, so I decided to remove Mike from the list of people who are authorized to see my album. Unfortunately, a simple temporary network partition can prevent, or even simple replication policies can prevent the propagation of this update to all the servers in the system. Now later on, if I try to add new pictures, it's very much possible that due to a simple load balancing decision or due to another network partition, this request is processed by a different set of servers than the ones that processed my earlier request. So later on, a consequence of this sort of this partitioning or this this eventual consistency is that later on if Mike tries to access my album, he will be able to access the pictures that I didn't want him to see. In contrast, if the system provided fork-join-causal consistency, then no node can process my second request without having processed my first request. And so my advisor will be prevented from seeing the pictures that I didn't want him to see. Yeah?
So in this example, all of your operations are going through one CloudPick node.
Right.
And all of Mike's operations are going through another node. Is that something that a provider like CloudPick has to ensure if they want to?
No. So the only requirement that you would, like basically the property that we provide, the fork-join-causal consistency, is provided to the clients of the cloud storage, so, which in this case are these servers.
So all the CloudPick servers are treated as one?
No. So they can be processed by, so these requests can be processed by the same client or can be processed by different clients. That does not affect the correctness provided by the system. The only, the one requirement, however, that I would like to point out is that these guarantees will only be preserved if the requests of the same user are processed by the same client, same user.
That's what I was getting.
Yeah. So I mean, there are multiple ways to sort of either enforce that or to sort of fix situations where that is not enforced. So if you can obviously maintain some kind of a session to ensure that the requests of the same user that are issued in a small time window are processed by the same machine in the CloudPick. But alternatively, you can also employ some cookies in the user's browser so that these cookies carry a short summary of the state that this user has seen. And later on, if the user now migrates due to a load balancing or due to a failure, if it migrates to a new machine, the new machine can ensure that it has seen the prefix that this client has seen from through a different client, through a different machine in CloudPick. So you can enforce those kind of policies in the browser or at the enterprise level to sort of make sure that the good properties you're getting from the cloud are also transferred to your users if you need to. Right. All right, so far I discussed the issue of which consistency should be provided by a system like Depot, which intends to be highly available and despite minimal trust. So next I'm going to describe some of the key techniques that Depot uses to achieve these properties. So at a high level, this diagram depicts the architecture of Depot. Data is partitioned into volumes, and each volume is replicated over a set of servers. We do not require overlapping read and write quorums to ensure high availability. Ideally, we would like Depot to be only running at the client in form of a library. However, our current prototype requires us to run code on both the client machines as well as on the cloud servers. But we have some ideas on how to change that, how to be able to provide most of Depot's properties with simple API changes in the cloud interface. So this diagram then depicts how Depot can enforce fork-join-causal consistency with minimal trust.
Previous slide. So which cloud service providers is your Depot prototype working with?
So right now we don't work with any. We have this code which we need to run on the storage server. So
because of this requirement, you can't use it with S3.
You can't. So the purpose of designing a system like Depot was to understand what properties can be provided, and then also derive from that understanding what are the API changes that are potentially needed to provide these properties in subsequent systems. So to some extent, we have succeeded in that goal because we sort of now understand better as to what would be needed from these storage service providers to be able to provide these properties. Or so basically, if you have all these API changes, you get all these properties. If you have fewer changes, these are the properties you get, and so on and so forth.
Will you be talking about that? Will you be talking about what those changes need to be?
Not in this talk, but I can talk about them offline.
Does this mean that the clients need to have some idea of how servers are laid out in the data center, or which ones are VMs on the same physical machine, which ones aren't?
No, because like the clients are only dealing with virtual machines, and they only talk for all the clients that need to do is they need to be able to send messages to a node with a given virtual ID and be able to sort of authenticate messages that are coming from coming from that virtual ID. Now, whether those messages are coming directly or they're coming through some other route is sort of like is not relevant.
So you have some table of metadata around the storage itself and what's gone where and how you...
So right now we also store some metadata, perform some checks on these storage servers because, again, like in Depot, we had this goal of providing extreme fault tolerance. So we even wanted to isolate one server from faults that happen in another server. But it's plausible that a deployment might want to weaken those assumptions and say that I'm willing to accept data from other servers in the same deployment without sort of checking them. And in that case, we can eliminate the need to actually store a lot of this data, perform a lot of these checks on the servers.
So, but it seems like the magic here is some consistency table that's maintained around all of the storage and all of the transactions. Is that roughly accurate, or is
I don't understand what consistency table.
Right, so the only way you would know definitively that one node's been updated and another unrelated node hasn't got that change yet is if you record those updates somewhere and then you check them.
Right, also like, the reason you don't need to do that is because you need to indeed record those changes in some form, but you don't necessarily need to know authoritatively what is the recent version of an object. And the reason is that we are not trying to provide strong consistency semantics. If you had a very strong consistency that like linearizability, then you would need to know that what is the most recent version of this object and where is it placed. On the other hand, if you're trying to provide weaker semantics such as causal consistency, you do not need to ensure that each get returns the most recent put that is performed to that object. It is sufficient to ensure that the get returns the most recent put known to the client who's performing the get. So the properties are weaker, and as a result, some of the requirements that you would have to enforce otherwise are not needed. Does that make sense? So
it does. Does it meet your criteria of making sure your boss won't see your pictures that you post?
It does, because if the clients are performing, if the same client is performing successive operations, then these operations will remain dependent on each other, and they will be observed in the same order. And that's how the criteria is enforced. That if any client who observes the second operation is guaranteed to also observe the first operation. So these two are dependent operations performed by the same client. On the other hand, if you would actually get more than that, and like I can try to explain some of the additional properties you get with this. But no, like Fork-join-causal consistency is enough to enforce those requirements. Yeah.
A quick question before you go on. When you say minimal trust, do you mean minimal in the mathematical sense or in the English sense?
In the English sense.
Okay. All right.
Yeah.
I don't know, maybe he has a lattice of trust.
All right, so let's see how we can enforce fork-join-causal consistency with minimal trust. So what we do is that we attach some metadata to each put. And logically, this metadata summarizes the history of this put. That is, all the previous puts that have been observed by the client before this put was performed. This metadata is then replicated to all the machines, all the clients, as well as all the servers in the system. It forms a part of their local state, and subsequent gets that a client performs are going to be sort of checked against this local state that the client maintains. And this is the key to enforcing consistency. And finally, before accepting new metadata, clients perform some checks to ensure that the new metadata is consistent with what they have seen in the past. So let me talk about what exactly this metadata is and what are the key checks that a node performs.
Updates are replicated at all nodes?
All the clients.
You mean eventually, or you're...
Eventually.
Yeah, because you can't possibly mean right everywhere, because
yeah.
You don't.
So basically, all the clients as well as all the servers that share volume will end up having some metadata for all the updates that have been performed in the system for.
Just the metadata, man.
Yeah, just the metadata.
So you don't push, but a client would like check for a metadata update.
Can fetch it on
before
demand.
to get, and that would be the way you ensure this consistency.
Yeah.
All right.
So let me talk about what this update metadata is. So it has some expected fields such as node ID, the key that is being updated, and the hash of the value that is being added. In addition, it includes two new fields. First is a version number that is assigned by the client who's performing the put. And second is a compact encoding of the history. And this encoding consists of a version vector and a hash, secure hash computed based on the local history. So nodes store this update metadata until it is garbage collected, and they compress it in form of a version vector. So let's see what checks does a node need to perform when it receives new metadata. So whenever a node receives a new metadata or new update, it performs two checks. First, it ensures that all the updates that are present in the history of this update are also present in its local history. So this sort of amounts to just performing a simple version vector inclusion check that the version vector included in the update is subsumed by the version vector maintained at the client. And in addition, we need to compute a hash to make sure to deal with situations where sort of like where corruption faults can corrupt the state. And secondly, we need to check that all the versions created by a given client are monotonically increasing, so that the client does not end up reusing the versions for different updates. So this system works fine if there are no arbitrary faults in the system. However, if a client experiences a loss of state or a corruption fault, it can lead to a problem. And this problem is called forking. So in particular, what can happen is, suppose that the client uses up versions up to version number 5, and then it dies or it loses its most recent state, so it sort of reboots and it starts reusing versions 3 onwards. So as a result, what's going to happen is that there will be two different updates, both with the version number 3. So in this case, if a faulty client F exposes these two different updates with the same version number to different clients, then what can happen is these two clients become forked. What I mean by forking is that now each of these clients has individually seen a consistent view of the system, but when taken together, the overall state of the system is not consistent. And this is so as a result of this forking, these clients cannot subsequently exchange updates, because if client A tries to send messages to client B which depend on the different version of update that it has seen, the client B will not be able to verify it. And similarly, if client B tries to send messages to client A will not be able to verify it. And this is not a new problem. The concept of forking was invented about like 10 years back by the Sunder system. And the key problem in all of these systems is that once the system gets forked, the system cannot attain eventual consistency, because these correct clients which have seen mutually inconsistent histories are logically partitioned from each other. They're prevented from exchanging updates from this point onwards. And this is a fundamental limitation which is not acceptable for a storage system to not be able to provide eventual consistency. So to address this problem, Depot has innovated on a new mechanism of joining forks. So what happens when a client observes that there are two mutually incompatible histories is that it pretends that the faulty node F is instead a collection of two correct virtual nodes, F prime and F double prime. So by doing this conversion, subsequently these correct nodes are allowed to exchange updates. But we have learned that this faulty node F has created inconsistent updates, and so subsequently we can evict this node from the system, and Depot includes mechanism for doing that kind of an eviction. So by doing this conversion of a faulty node into multiple virtual correct nodes, we have basically converted a corruption fault or an arbitrary fault into logical concurrency, which these systems are already prepared to handle. All right, so in this part of the talk, what we learned is what it means to minimize trust for correctness, what consistency Depot provides to achieve its goal of minimal trust, In particular, we discussed a new consistency mechanism called fork-join-causal consistency that is strong enough to be useful, yet weak enough to be enforceable in depots under depot's strong, weak assumptions. And the key idea here was to be able to reduce failures into concurrency. And in addition to all of this, we provided a protocol for enforcing fork-join-causal consistency. So next, I want to talk about availability. So let's try to understand where does trust exist for availability in existing systems. So as before, in existing systems, a client trusts that the SSP will remain available whenever it wants to access data. Similarly, for typical state machine replication systems, the client expects that a set of nodes will be available whenever it wants to access data. In contrast, the goal of depot is to enable the client to define a replication quorum for each object so that the client can control its replication policies. And in depot, we want to be able to ensure that an object remains available as long as there is at least one copy of this object present at any of the available machines. So for example, a client can define that it wants to replicate its data onto multiple SSPs, and so the data should be available if either one of those SSPs has not failed or is available. Similarly, a client might decide to keep a local copy of an object in its data store, and in this case, the data should be available if either the local copy or the SSP is available. So this might seem simple, but the main reason we are able to achieve this goal is because we have eliminated the trust for consistency. In contrast, in traditional quorum systems, if we try to apply this approach, we risk reading inconsistent or stale data. So let me illustrate why a problem can arise if we didn't have the support of minimal trust for consistency. So suppose that a client performs an update and pushes a route to one of the SSPs, receives the notification from the SSP that the write is completed. Now later on, if the SSP fails and the client tries to retrieve this album from the backup source, which could be a secondary SSP or its local data store, in this case, the backup store may not have a copy of the object that the client just pushed to the first SSP. And the SSP will end up returning that the album is empty. Now, absent depot's mechanisms for detecting correct data from incorrect data, the client will simply accept this response from the second SSP and do further processing based on this response, which will lead to the violation of the consistency requirement that we want to provide, which is that if the client performs a put and then performs a get, the get should reflect the result of the put that it just performed. However, if we have deep... Sorry?
So to have that property, you've got to have somebody else that knows what to write. If you write something to one place, nowhere else, there's no record of it anywhere else, and that place forgets it, then it's as if it never happened.
Right, but
right?
even
so you're storing this history vector on the client too, right?
Well,
it's got to be somewhere.
Sorry?
It's got to be somewhere, or you can't have this property.
Right. So what I'm saying is that it's not easy to simply replicate data on multiple SSPs if you don't have mechanisms to be able to detect that which copy is acceptable and which copy isn't. Depot indeed does that, but if you didn't have those mechanisms, if you used a simple client.
I guess I'm going back to how Depot does that. Where is the knowledge stored?
At the client.
It's at the client. Okay.
Yes.
Right.
So if the clients have this knowledge, and if the clients are able to separate correct data from incorrect data, then the client can distinguish and identify that this response is potentially stale or incorrect, and it should not be processing this. So far I discussed how Depot minimizes stress for availability. Next, I'm going to talk about durability. So for durability, we want to be able to make sure that the data eventually becomes sufficiently replicated. So we have enabled the client to define where all it wants to replicate data. But for durability, our goal is to ensure that this data eventually does become replicated at each of these machines. What this means is that we need an agent in the system who's responsible for pushing the data to all the replicas at which you want to replicate an object. This agent could be the client who's performing the put. It could be the SSP configured to sort of push the objects to another SSP, or it could be some background job which is reading data from one SSP and pushing them to another SSP. In either of these cases, we're putting some trust in that agent to correctly perform this task of replication. And this is the trust that can lead to compromise of durability. In particular, so far in the system that we have discussed, every time a client reads or writes an object, it is trusting that the replication agent has performed replication for this object correctly. If the replication agent fails to fulfill this task, it can lead to a situation where we compromise durability. So let me illustrate how that can happen. And let's take the example of client performing the put. Let's consider a situation where we designate the client to perform this task of pushing data to all the SSPs. So suppose that the client, in the normal case, client ensures that it has pushed the data to both the SSPs. So if another client reads data from first SSP and later on that SSP fails, the client can easily access the data from second SSP. However, there might be a situation, there might be a small window of time when the client has pushed the data to first SSP, but it hasn't yet pushed the data to second SSP. At this point, the data is visible to all the clients who are accessing the first SSP. So another client might still end up reading this data, but the data is not sufficiently replicated. And later on, if this client fails, the data may not ever get sufficiently replicated. Furthermore, this object is sort of living dangerously at this point, because if this SSP now fails, the durability of this object will be compromised. So our goal in Depot is to be able to ensure that any object that is read or written by a correct client remains durable as long as some replica in the client's sufficient replication quorum survives. So if I've designated my object to be replicated at both two SSPs, this object should remain durable if it has been read or written by a correct client and one of those SSPs survives. And the way we are going to achieve this goal is by minimizing the trust that is needed to enforce the client's deployment replication policy. So the logic for this is relatively simple. All we need to do is to add some receipts to the system. So in particular, what we do is that every time the client stores data on one replica, the replica issues a receipt certifying that this data has been durably stored on that replica. These receipts are then attached to the metadata associated with an object, and they're propagated throughout the system using the mechanism that Depot provides. Now, whenever a client receives an object, it ensures that it checks if the object is sufficiently replicated or not. If the object is already sufficiently replicated, the client does not need to do anything else.
How does it check?
Because the object has associated receipts.
I see. It checks its receipts.
Right. So it will check if the replication policies require replication at two SSPs. The client can check whether the object is already replicated at two SSPs or not.
It has to go back and request those receipts.
No, they're attached to the metadata, so the client gets them.
I see. When the metadata updates come, they
Yeah.
contain receipts as well.
Yeah. So this is the easy case where the object has been already sufficiently replicated, and the client reads it, so the client sees that the object is sufficient, so it doesn't need to do anything in this case.
So after you write a second copy, you need to go back to update the first copy.
Right. Yeah.
That just means that the write takes longer.
No, so the write is complete as soon as you perform the first operation at the first SSP.
But
And then
you're
doing some extra work which you can piggyback you're doing some extra work for that write, but the write is complete and visible as soon as you perform the first operation. So, however, when a client receives an object and it sees that the object is not sufficiently replicated, then the client requires a copy of that object along with whatever insufficient receipts there are. And the client decides to store this copy until it learns that the object becomes sufficiently replicated. So the client ends up storing this copy locally, and then it can continue processing. And later on, when it learns that the object is now sufficiently replicated, at that point it can discard the copy of this object.
If the client doesn't trust its own local store to become sufficient, it might not want its writes exposed until sufficient receipts.
Right, that's also a policy, but so let me actually I come to that in the next slide. So receipts also, this approach of minimizing trust for durability actually helps us sort of address a fundamental trade-off in geographically replicated distributed systems. So in these systems, you have this trade-off between being able to complete an operation with low latency. And what I mean by low latency is the latency smaller than the wide area replication delays, and durability in presence of data center failures. So let me illustrate what the problem is. So whenever the client sends a request to to a server in one data center, the server has two choices. It can either respond back to the client before ensuring replication to other remote data centers, in which case you get low latency. But at this point, the write is not durable if data center failures can happen. In contrast, if the storage server waits before receiving responses from all the remote servers, in this case the object is certainly durable if a data center failure happens, but the request took much longer time, and the operation is not low latency. In contrast, with a mechanism like depot, when a client sends an object to the first server, the server can respond back with a receipt saying, I'm replicating this object locally. The client at this point holds on to the object instead of throwing it away as is done normally. And later on, this operation is still low latency because the server does not need to replicate data to all the remote data centers before responding back to the client. However, if later on this data center fails, the client still has a copy of the object. And as a result, the client can push this copy to these remote data centers and ensure that the object becomes sufficiently replicated and is durable.
The client can push to the remote.
The client can push. So this approach is desirable because you get some implicit fault tolerance because the client is typically logically or physically separate from the servers. And in some sense, the client is also controlling its own fate. So if the client survives, the object will also survive. If the client fails, then the object will fail.
Not addressing conflict resolution then?
So conflict resolution is a problem that is, so this talk is not really about conflict resolution because that problem arises irrespective of whether you use this mechanism or not. Right. Because we're...
But you've introduced some other last ends because...
No. So actually so for conflicts, actually the approach that depot adopts is that it returns all the concurrent writes that have been performed to an object. And with each write, you can associate whatever extra metadata you would want to associate to ensure the conflicts are resolved properly. So for example, you can attach a timestamp and then pick up a winner based on that timestamp, or you can sort of like merge the concurrent writes in some meaningful way based on the application semantics. So we're not introducing a new last writer here because the timestamp that you would associate here would be the timestamp that the client assigned to this object when it performed the original operation.
Right, you're just adding an additional staleness factor.
Yeah, it does increase. It's possible that if a data center fails, you end up having more staleness than you would see otherwise. So later on, when the client gathers the receipt from this other remote data centers, at that point it can discard this copy of the object.
The client is, say, not in the data center that it's trying to write to.
Even if it is within the data center, it still gets some additional fault tolerance because the services may indeed be isolated.
It can be in the data center, it's just got to be aware of all available regions.
Well, what I'm saying is if it's in the data center, then it's correlated with the data center.
The failure could be correlated, but the argument, again, there are two arguments. One, that they could be logically separate entities, and secondly, if the client also fails, then it's sort of like losing all recollection of what it has done, and so maybe it might be acceptable. I'm not arguing that it is acceptable, but it might be okay in that circumstances.
What if a client writes object A with intentionally low durability and then makes a dependent write to B with high durability? Does the high durability of B extend to A? It won't. Well, because I could see that if A becomes unavailable, now B, this supposedly high durability thing, everybody will say, well, I can't process B.
So you can still process B, just that if you're writing something with low durability, maybe you're okay with the object losing that data. That would be your intent. So if for example for object A, I specify that it's enough to replicate that object at any single data center, whereas for object B, I require that this object should be replicated at 2 data centers. So what might happen in that circumstances is that you might lose object A, but you still have access to object B. So and presumably because you were writing A with low durability, you should be prepared to handle the situation where you lose object A and perhaps are able to recreate a copy of object A through some other mechanism.
But how does depot handle? I mean, depot just sees, oh, B has this pointer saying, you know, back from B to A, and it'll say, well, I can't provide you B until I.
No. So B does not include a pointer to A. I mean, it logically does, but B includes a pointer to A's metadata, which will be available. The only thing that you'll end up losing is A's data. So you won't be able to read A, but you still have all the information that you need to enforce consistency. So this is a graph that depicts the situation where in a local cluster we killed all the cloud servers at about 220 seconds, and it shows that depot's puts continue functioning even after the servers have been removed, and they function with low latency because they recognize that the SSP is down, so they don't need to go to the servers anymore, and they periodically keep on checking if the SSP has come back, and that's why you see like these latency spikes happening in between. At about 660 seconds, we bring back the SSP, and sort of like the clients then at that point push back the state to the SSP and starts working from the storage service again. So in this configuration, we use the local backup as local backup and one SSP as our deployment. So next, let me talk about how much does it cost to provide properties that depot provides. In particular, I'm going to talk about latency, resource utilization, and the dollar cost of building a system like depot. So the test bed that we used consisted of 8 clients, 4 servers. We were performing about 1 request per second, and each volume contained 1,000 objects. So just as a reminder, these are the sources of overheads in depot. We are attaching some metadata to each object, and this metadata consists of a signature, potentially receipts, a partial version vector, a history hash, and a data hash. In order to accept a metadata, a node performs a SHA-256 check, an RSA verification, history check, and then receipt checks. And then to perform a get, a client performs a SHA check, SHA-256 check. So this diagram depicts the latency of several variants of the baseline system that we have constructed. So in order to provide comparison points, what we did was we constructed several baseline variants. And these baseline variants try to emulate cloud storage by disabling the replication on the clients of the metadata and disabling all of the checks that depot provides. So for example, the base system does not have any data at the client, and it does in base system clients also do not perform any checks, and the servers also do not perform any checks. Whereas in the hash system, the clients compute a hash of the data and attach it to the object before storing it, and then when they read, they verify the hash. And similarly, in the sign, the clients sign the object before storing it, and then check the signature when reading it. The depot minus R version does not include the receipt receipt code, receipt logic of depot. And the main reason for providing this variant is that in depot we use cryptographic receipts, but for many deployments it may be acceptable to instead just use sort of like receipts that just have plain text information, because if nodes trust each other to provide the right information, then that might be acceptable, and many of the overheads that we incur due to cryptographic operations may be eliminated. So the key thing to note here is that the overheads for gets is very, very small, because the only extra computation that the client needs to do is to perform a SHA-256 check on these gets. In contrast, for puts, the overheads are high because we're performing several cryptographic operations. In particular, in the complete variant, we need to perform two SHA-256 signatures on the critical path, and that's why the cost of the full complete depot version is significantly higher. But like I said, if you want to, there's a potential to remove a lot of these cryptographic operations and reduce the overheads of depot significantly. RSA. 1024-bit, I think.
It's taking 5 seconds to do 2.
Yeah.
Or 5 minutes.
Yeah, each signature costs about 4.4 milliseconds, I think.
Library, make that go faster.
Yeah, we're using Javas. Yeah. So next I want to talk about the resource utilization cost of depot in comparison to these other variants. So in this bar graph, I depict the normalized cost of depot in comparison to these other approaches. And in particular, I compare 3 resource utilization metrics. We compare the network utilization between client and servers, the CPU utilization at the client, and the CPU utilization at the server. So for gets, as we can see, the overheads of extra network cost is sort of negligible. And similarly, for at the client, the extra cost primarily results from the extra hash computation that they need to perform. The CPU utilization of the server was very, very small, so it's pretty much random.
How big is the data you're moving for this?
Sorry? 10 kilobyte objects.
10 kilobyte objects.
Yeah.
And your network overhead looks like 0, but you ought to be moving, when you're moving 2 signatures.
It's about, so the basic metadata without the receipts is about 300 bytes, but we don't add the cost of that metadata to gets. We instead attribute it to put, because we are replicating that, because each client ends up storing that metadata. So we, when we are doing in the accounting, we add that cost to the cost of a put instead of adding it to the get.
So you're sort of assuming that the objects you're putting are rather large, and so the metadata.
Yeah. So this, so if you have small objects, indeed, like the cost of the system may be prohibitive for. In this case, we looked at 10 kilobyte objects. If you have smaller objects, say like 500 bytes or smaller, then you will end up paying a lot of cost.
Is the metadata fixed size, or can this version vector vary?
So version vectors are fairly fixed size, unless you end up like sort of. I think in most cases you can argue that the version vectors are going to remain of the fixed size.
Writers, which in real life doesn't happen.
So also, like the other situation is, the other reason why version vectors are fixed, because we instead of using encoding attaching a complete version vector, we only each update carries an incremental version vector over the previous update. So because the system is processing updates in a consistent order, you can remove the information that has already been there in the previous version vector. So you only encode new, but asymptotically, that does not change much. So this is the overheads for put, and as you can see, both depot as well as depot without receipt incur about 20% cost of metadata transfer between client and servers. So each of these is probably 20%, because we have about 300 bytes and we're transferring 10 kilobytes. So that's about 2 kilobytes of metadata transfer for 8 clients.
The other interesting thing is, if you're really storing objects in size, you've got to replicate the metadata everywhere. So you wind up using, you wind up using 20 or 30% of this. You can only have cloud storage that's 3 or 4 times larger than your local storage, because your metadata winds up being a third of your total. I mean, you lose a lot of the advantages of cloud storage if your objects are that tiny.
Right.
Because you have to have the metadata replicated.
Yeah, you need to sort of build.
On the other hand,
we don't lose the advantages. It just costs a lot more.
It costs you a lot.
You got to have local storage. You can only multiply the size of your local storage by 3 if you have 10K objects. And of course, the answer is don't have 10K objects. Right.
Yeah. So again, like the storage cost in the client is high, because in a traditional system you don't have to store anything in the client, whereas in the context of depot we need to store this metadata at the client. And furthermore, like in this deployment, we were also storing. The client was configured to store a copy of the data that they create, so that because we are using the local backup approach for ensuring durability. So there was one copy stored in one SSP and another copy stored in local data centers, and that's why the additional cost comes is even more significant. The CPU utilization of the client is high because you're performing receipts, you're performing checks for these receipts, so all of that adds up. And similarly, the CPU utilization of the server is particularly high for the receipt variant, because the server is now doing these cryptographic signatures for this variant. So next we want to look at how much does it actually cost in terms of the dollar amount to implement a system and run a system like Depot. So to do that, we basically convert all of these resource utilization numbers using some sort of some cost numbers that we gathered from existing pricing. So what this tells us is, as expected, to perform a terabyte of gets, you pay very little extra cost, less than 5%. But to perform a terabyte of put, you almost pay 100% of, you double the cost needed to perform a terabyte of put. This is for 10 kilobyte objects. And for storage, you again pay like about 20% extra cost because you're storing metadata as well as data, extra copies of data. So once again, basically the point is that these costs are high, but they're not so high. They seem acceptable to me. I don't know if they'll be acceptable to clients or not, but again, these overheads can be dramatically reduced if you remove cryptography from.
Kilobyte objects.
Or you don't have 10 kilobyte objects.
Which you won't, right? I mean, every time we've looked at, say, file system stuff, what you find out is, you get a bunch of small objects, your mean object size is going to be orders of magnitude bigger than that.
Yeah.
Right? And so your overhead is fixed per object. So you're probably making yourself look worse than you would in
file systems, you said?
File systems. If you look at local file systems, what you find out is that the mean file size is hundreds of kilobytes to megabytes. Because there's a tiny number of giant ones.
Isn't a more direct comparison database systems, though? I think this is designed more as a stand-in for a database than a stand-in for
this provides much low-level interface, so it's...
Right. Individual database records are going to come in under 10K, probably.
Well, is there any data from Amazon and how big S3 objects are?
Well, they're expected to be several gigabytes.
For S3, but Dynamo is a better.
Yeah, Dynamo is much smaller. All right, so in this part of the talk, I introduced a system called Depot that takes this approach of minimizing trust, and we showed how, despite minimal trust, we can achieve some very strong properties, stronger properties than those provided by existing systems. So in terms of related work, the key point to take away here is that there's a lot of related work that are focused on building systems that minimize trust or improve availability, but the main distinction between all of these systems and Depot is that Depot is designed to really, really minimize trust, whereas all these systems sort of go halfway they try to reduce trust in the system, but don't entirely eliminate it. And similarly, they don't achieve the same level of availability that Depot promises to achieve. So, broadly speaking, how this my research is focused on addressing sort of the trade-offs, investigating the trade-offs between consistency and availability and fault tolerance. So what Depot works sort of tries to do is to try to understand what is the practical limit of properties that can be provided if we want to hold on to availability and fault tolerance. In contrast, I've also done some theoretical work in trying to understand what is the theoretical limit of properties that can be provided with high availability and fault tolerance. And what we ended up showing was that a variant of causal consistency is really the optimal you can get if you want to provide high availability. And similarly, we have some results that are not as strong for environments where you also want to minimize trust in addition to maximizing availability. So in the next part of the talk, I'm going to briefly touch upon a system that I'm currently, some ongoing work, which is focused on answering the other end of the question, which is that if you want to hold on to consistency, if you always want to be able to support ACID transactions, then what is the best availability you can get? And in particular, we are designing a system called SALT that integrates the ACID transaction with the base approach. So next I'm going to talk about how do we mix acid and base in the system called SALT. And it's not a chemistry talk. So we all know the benefits, we all fully understand the benefits of ACID transactions. They're used pretty much everywhere to encode business logic, to perform banking transactions, and so on and so forth. And they provide these sort of very attractive properties of atomicity, meaning that the entire transaction, either the entire transaction completes or no effect of the transaction is left. Consistency, meaning that the database transitions from one consistent state to another state. And isolation, meaning that the transactions do not observe the intermediate state of other transactions. And durability, meaning that the effect of completed transactions remains durable. So the reason distributed databases have low availability with ACID transactions is because in order to perform an ACID transaction that spans multiple components, you want each of those components to be available and reachable. So for example, if you want to perform a transaction that includes two components x and y, if either x is down or is unreachable, or if either y is down or unreachable, your transaction will not be available. So in contrast to this ACID approach, there is the approach called base approach. And unlike ACID approach, the semantics for this, there is no well-defined semantics for this base approach. There are really like various variants of this approach. Different systems implement various flavors of base approach. And the only underlying idea behind this base approach that is sort of common to each of these approaches is that we're trying to compromise consistency to get better availability and better performance. So this approach can be applied on top of an existing database by using the database to perform some very minimal tasks, or it can be used to on top of some NoSQL systems that are there, or like consistent data stores like Bigtable and so on and so forth. So the main idea is that the application now has to deal with the task of enforcing a lot of these properties that previously were being enforced by the system. So the reason this approach improves performance is because the application does not have to deal with providing the transactional properties anymore. Instead, the application can issue each one of these operations separately, so the system remains available. If I have to update x, the system will be available if x is available. And similarly, when I have to process y, the system will be available when y is available. So I don't need simultaneous availability of both x and y in order to be able to perform the same computation as I was doing before. So this comes with better availability and better performance because you don't need to perform the two-phase commit. You don't need to hold the logs throughout the duration of this transaction. However, it also complicates programming because it's possible that while you're executing, while a particular operation is partially completed, some other operation can come in between and access this inconsistent state. So typically you would handle this situation by signaling to the application, or the application might signal to the user that the result of some of the recent operations may not be reflected in the result that I'm showing you. So for example, if the user is trying to see its account balance, there might be a notification or there might be a disclaimer that this may not reflect most up-to-date balances. So there is again this conflict between ACID and base. Both of them have their advantages. ACID provides simplicity of programming, but at the cost of availability. And base provides sort of availability and high performance, but at the cost of ease of programming. So in this work, we are trying to ask the question that can we actually provide the benefits of both of these approaches without being vulnerable to their limitations. And that's why we are building the system that combines this ACID approach, that attempts to combine this ACID approach with the base approach. And this seems like a good thing to do for two reasons. First, most of the workloads actually do not consist of performance critical transactions. Most of the time, you have very few transactions for which you care about performance, and a lot of other transactions which are performance oblivious. So if you're able to combine these two approaches together in the same implementation, I don't have to rewrite all of those performance oblivious transactions, and I just need to focus on rewriting and doing more work for the transactions that are performance critical. Secondly, this also provides an incremental adoption path. So think of an enterprise that gets acquired by Microsoft. So it's going to gradually see some increase in workload, but the increase will not happen overnight. So as a result, the enterprise can incrementally identify the bottlenecks in their workload and fix those bottlenecks over a period of time rather than having to atomically transition from an ACID system to a base system. Now, there are various challenges in providing ACID in sort of supporting both these approaches simultaneously. I'm going to talk about one particular challenge next. So the key problem is that the presence of base sort of like paradigm in conjunction with the ACID approach can kind of like corrupt the consistent view that the ACID systems expect to see. So suppose that we have this transaction that we're trying to execute using the base approach, and we have executed the first part of this operation, first part of this transaction. And now in between an ACID transaction comes in, and it tries to read both x and y. So it would expect that that the invariant that the sum of x plus y remains constant should be preserved, but because it is seeing the incomplete state of a base transaction, the invariant will not be preserved. So to address this and other limitations, we basically introduced a new abstraction that is called base transaction. So base transaction has a similar structure as ACID transactions, as we can see there, and it provides a number of properties which are very similar to the properties you expect from ACID transactions. In particular, they provide a notion of atomicity, which means that the entire transaction will eventually be executed to completion. It provides durability for completed transactions. For integrity enforcement, it introduces exceptions. So every time the base transaction tries to perform an operation that violates the application's integrity constraints, it results in an exception which can be handled by the base transaction locally. And it may contain ACID transactions to simplify programming. The three key properties that it provides in addition to these other good features is that presence of base transactions does not affect the correctness of ACID, concurrently executing ACID transactions. Furthermore, it also does not affect the performance of concurrently executing base transactions. And I'll talk about this in the next slide as to why this might be a problem. And finally, it ensures that we're able to provide the same availability and performance as we expect of the base transaction using this base transaction primitive. So let me give you a sense of two key implementation ideas that we use to implement base transactions. So first of all, base transactions are serialized as a sequence of atomic transactions. You can think of them as an ACID transaction, but they're not strictly ACID transactions for technical reasons. So they're going to be, in the overall execution history, base transactions are going to appear as several small fragments. The same base transaction would appear at multiple points in the overall serialization history. Now, in order to ensure correctness of the ACID transaction, these base transactions are going to acquire some tainted locks, which are going to mark that these objects are being modified by an incomplete base transaction. So the result of these tainted locks is that while other concurrently executing base transactions can come and access the intermediate state of other base transactions, ACID transactions will be prevented from accessing the incomplete state of the system, incomplete state of a base transaction. Now, to ensure that the ACID transactions perform the same, give the same performance in presence of base transactions, we need to add a few more mechanisms. But the key problem here is that because we are going to execute the base transaction as a series of small atomic transactions, and each one of them will require performing a disk write. So the duration of a base transaction will be, if a base transaction consists of 5 separate mini transactions, then the duration of a base transaction will be basically 5 times larger than the duration of equivalent ACID transactions, because in an ACID transaction you're going to perform all the disk writes in parallel. And as a result, without the mechanism that I'm going to talk about, the base transactions might significantly impede the progress of ACID transaction by blocking them. So instead, what the key idea that we use is we try to break down the commit of transactions into two parts. First is the consistency commit, which basically ensures that we still perform the two-phase commit, we release all the logs, but the data is stored only in memory after the first commit. and then later on we perform a second commit, which is the durability commit, which happens asynchronously at each of the in a distributed fashion, so it does not require any coordination between various nodes. Each node can individually flush its data to disk, and then there is a recovery protocol to ensure that when we recover the system to a consistent snapshot. And then there is some other logic to ensure that only the result of committed and durably commit transactions are exposed to the application, so that the application does not see the effect of a transaction which has committed, which has released its logs but has not yet made it safely to the disk. So in summary, in this part of the talk, I discussed an approach to combine ACID transactions with base transactions, and to do so, we introduced a new primitive for base transactions, which enables us to isolate the intermediate state of base transaction from concurrently running ACID transaction while preserving their correctness as well as performance. These are some of the other publications that I've had, and I'd be happy to talk about any of this related work if you like. So in conclusion, my research has explored extreme points in this consistency availability trade-off. With the deeper work and with some theory work, I've explored the point where we are trying to maximize consistency, where we're trying to maximize availability, and trying to see like what is the best consistency you can get. With my recent work, we're trying to investigate situations where you want to hold on to the strong consistency in form of ACID transactions, and trying to and seeing how can we improve on the availability of these systems. So with that, I'll be happy to take any questions.
We asked him in line.
Right.
For Salt, I mean, do you have some specific applications in mind, sort of full customers for the system?
For the first part of the system or the second?
The first part.
For the depot?
Actually, Salt.
For Salt? So we're looking at, for example, we're looking at TPCC benchmark, and we also looked at Rubis benchmark. So pretty much anywhere you're trying to compute the index, it's usually acceptable to. So there are a lot of workloads that we have looked at where it would make sense to combine ACID with base. Some examples of those workloads are situations where you're trying to compute an index, but the consistency of index is not critical. So for example, when you add a new item to eBay to be sold on eBay, the item has a category. So you would normally want that when people search for that category, the item shows up, but it's usually acceptable if the item doesn't show up instantly and instead shows up a little bit later. Similarly, you can also actually use the base approach to perform very quick e-commerce checkouts, because one thing that I didn't discuss about these base transactions is that they include a notion of primary transaction, where you can specify that I want this transaction to be executed right now, and then the rest of the work to be done asynchronously in the background. So if a customer tries to purchase an item, you can have the stock quantity of that item decremented synchronously, and then you can try to charge the credit card and update the order and try to do all the background tasks in the remaining base transaction. So that's also where it would make sense. And similarly, like in these banking applications, it might make sense to decrement the balance first using a synchronous primary transaction, and then try to increment the balance of the destination account later on in the background. So pretty much anywhere you can think of relaxing consistency, or you can think of being able to perform commutative operations, you can benefit from the base approach. Yeah.
So I have a question about depot with the gets returning multiple versions of an object.
Yeah.
Does that only happen because of forks, or are there other?
No, it can happen due to legitimate concurrency as well. Because if two clients concurrently try to update an object, it can certainly result in concurrent versions of an object, just like it can happen in Amazon S3. In Amazon S3, however, when you do a get, the system automatically tries to resolve the conflict for you by saying that by using some best effort timestamps. So you can also overlay that kind of an approach on top of depot to say that I just want to see, I'm going to associate some timestamps, and I just want to see one of the versions which has the highest timestamp, which might make sense in some applications, but in other applications it might make sense to be able to see all of the concurrent versions and try to merge them in some ways. So basically we leave it out, and you can layer it on top of depot in whatever approach makes sense for your application.
Okay, well, thank Prince again.
Yeah, thank you.